Hi, my name is Stella, and I'm going to talk about our ongoing work on formally ruling out timing side channels in synthesizable hardware. This is joint work with Thomas, Clément, and Adam. The big picture motivation is that we often want to run trusted security critical code on the same machine as untrusted code without leaking secrets. Modern computing platforms run programs from a number of different stakeholders. For example, we routinely run cryptographic code on the same machine as different applications under an untrusted operating system. We can decompose this problem into two parts. First, attackers should not be able to observe secrets from trusted code, nor interfere with trusted code due to being physically co-located on the same machine. And second, security critical code should not itself leak secrets when executing independently. To achieve the first property of isolation, we typically rely on primitives such as virtual memory and process isolation provided by the operating system. In situations where we do not trust the operating system, we might use enclaved execution environments such as SGX that provide hardware support for isolation. A programmer that wants to achieve the second property might use auditing or constant time programming. But the problem is that these techniques are not enough. As we heard from previous talks, the isolation and constant time guarantees that can be enforced by commodity hardware are simply too weak. And subtle microarchitectural timing side channels have extracted secrets from co-located processes, enclaves, and code that is deemed constant time. For performance, we share microarchitectural resources, but when we share finite resources, this ultimately ends up to interference and a wide attack surface. Caches are a well-known and well-studied example, but there are sources of microarchitectural timing side channels that occur there are even more subtle sources of these timing side channels. For example, port contention, contention for functional units, and DRAM bandwidth. Recent work such as MI6, upon which our work is based, tries to restore isolation at the microarchitectural level by spatially and temporally partitioning all resources. As we heard from the previous talk, constant time is not enough. Constant time assumes a sequential ISA semantics, but under speculation, this is not enough. And previously, a lot of work on speculative constant time hasn't really addressed BTBs and return address stacks until the state-of-the-art work that we just heard from the last talk. Ultimately, the problem is that there's a mismatch between the sequential ISA semantics that the programmer would like to reason about and the complex microarchitectural designs that exist in practice. And these designs are too complex for localized patching or informal analyses. This brings us to our proposal, which is to apply formal methods. Our goal is, our pitch is that we should build confidence in mechanisms that eliminate microarchitectural leakages by formally ruling out timing side channels in real hardware and software. As a standard in the formal methods community, we value having a small TCB with end-to-end guarantees that are as far apart as possible. As such, we think it is valuable to do verification on real synthesizable designs as opposed to just verifying models. While we think that models are useful as intermediaries, mismatches between models and reality are common sources of vulnerability. This approach has two steps. The first step is the focus of the rest of this talk, which is doing hardware verification of strong timing isolation. This means that programs located on the same machine observably behave as if they were running on separate machines connected only by a network. So at a high level, the attacker can communicate with the victim only through a dedicated API. They can observe public interactions with their associated timestamps, but they cannot infer information through shared resources such as buffers or caches. Ultimately, the point here is to make a much narrower attack surface so that the programmer does not have to reason about complex microarchitectural details. The second part is future work, and it's to compose this with a hardware-software contract for speculative constant time. So reading the turnstile symbol as the word satisfies, we want to say that assuming hardware satisfies the contract and software satisfies the contract, then running secret code on a machine is equivalent to the attacker as running code without secrets. After we compose the two together, we'll get the final end-to-end guarantee that running secret code on a machine co-located with an attacker is equivalent from the perspective of the attacker to running code without secrets on its own machine. I'm going to give an outline of our work on hardware verification of strong timing isolation. As a case study, we implemented an embedded class RISC-V machine that provides hardware support for isolated processes. We call these enclaves, but they're much simpler than the enclaves that you might be familiar with. This is implemented in COC and has a formal cycle-accurate semantics down to the circuit level. We specify enclave behavior using a specification that's parameterized on the implementation and avoids design-specific details. So the operation of running enclaves is modeled as basically running on air-gapped machines, and context switching is modeled as throwing away machines and getting a new one. The top-level theorem that we're interested in is cycle-accurate trace equivalence of the MMIO. This captures the idea that from the perspective of the external world, the implementation and the specification behave in the same way. Finally, we developed a modular proof strategy that crucially sidesteps the need to prove functional correctness of, say, the processor. So we think that we can replace our embedded class RISC-V processor with a more complex speculative out-of-order processor with minimal changes to our proof and specification. On to our implementation. We implement a 2-core RISC-V machine that's pipelined with a hardware security monitor, a memory subsystem, and a single port VRAM. This machine provides hardware support for enclaves here, green, yellow, red, and blue. To achieve this, we spatially and temporally partition our VRAM. So there are some regions that are exclusively owned, and there are some regions that are temporally partitioned, the mailbox regions, such that ownership changes on context switching. Enclaves communicate via these mailbox regions or via MMIO. The processor is like a standard RISC-V pipeline processor with additional complexity that its job is to purge on context switching, so its resources are exclusively owned by the active enclave. It sends memory requests and hypercalls to the security monitor, whose job of the security monitor is to enforce architectural isolation. So to do this, it basically maintains a table mapping each core to the memory regions it's allowed to access. Here, core 0 is allowed to access the green region and the green and red mailbox region, and core 1 is allowed to access the red region and a shared UART, the exclusively owned MMI UART region. The job of the memory system is to arbitrate access to the single port VRAM to prevent contention-based side channels. Importantly, everything in this blue box here is implemented in Koika, which is a hardware description language that is embedded in COC with cycle-accurate semantics. So there's a verified compiler from Koika down to circuits, which means that the properties that we're proving extend down to the circuit level. Finally, we model the external world as being an abstract function of the history of the previous MMIO outputs, which lets us reason about all possible behaviors of the external world. Now, how do we specify this machine? Enclaves basically have two states. They're either running, and they should be isolated when they're running, or they're context switching. We model we model isolation when running as air-gapped machines, and context switching as throwing away a machine and getting a new one. So on the left, we have the implementation from the previous slide, and on the right, we have the specification. The spec tracks the enclave configuration of the cores, and we capture this idea of isolation by splitting up the machine into two independent machines. So we have the green machine and the red machine that are separated with the unused memory regions, with no connection to the unused memory regions. So each of the machines can only access the memory regions it's allowed to access. At each cycle, input from the external world is given to the machine with some subtleties about which input goes where. So here, the input from the UART is given to the red enclave. And importantly, at each cycle, the state machines take a step independently to generate a MMIO output, which we merge together to generate the specifications output, which should be equivalent to the implementations. Hopefully, we can see here that this design makes the isolation and information flow fairly explicit, with each enclave basically acting independently and communicating only via the outside world. On to context switching. So on the top is the implementation, and it's trying to context switch from the green enclave to the blue enclave after it does some purging. In the specification, we model this as throwing away the old machine and copying over the old memory region, so the green and the shared green and red region are copied over. And then we initialize a brand new machine with only the memory regions allowed to access. So it's initialized with the blue region and the shared red and blue region. Now this brings us back to the situation from the previous slide where we're running in isolation. And this captures the notion that we initialize our machine with the initial data, but once this happens, it basically runs in isolation. There's some subtlety with our spec where we actually don't want the spec reader to reason about implementation design details, so we actually can replace the enclave, little machines with black boxes, and all we care about is that the machine behaves as a function of the initial input and communication with the external world. Finally, the top level theorem that we care about is MMIO trace equivalence. This is slightly different from traditional ideas or notions where we care about memory, loads, and stores, with the idea being that we don't care if the attacker can observe secrets. As long as it cannot exfiltrate them, we are safe. I'm not going to go into too many details about the proof methodology, but I did want to highlight one point, which is that in our method, we sidestep functional correctness. So after we decompose our proof obligations into different components, we realize that the proof obligation for the processor basically amounts to purging on context switching. We don't care that it implements RISC-V correctly, and this drastically simplifies the proof and makes the verification problem of verifying synthesizable hardware much more tractable. This lets us argue that we can replace our embedded class processor with a speculative outer order processor with minimal changes to the proof and specification. So in conclusion, we presented our work on verifying isolation for synthesizable hardware. But this is not enough to achieve the bigger goal of secure execution on shared machines. Ultimately, we need to compose with guarantees about software. This composition is not necessarily straightforward. For example, one challenge we had is that the time it takes to purge is actually dependent on microarchitectural data, and thus can be a source of timing side channels. Lastly, it's interesting to ponder over what the future of timing side channel freedom should look like. So you can imagine a security engineer that's writing some code in some high-level language with formal leakage trace semantics, and then a leakage trace preserving compiler generates RISC-V code that is either verified or validated to be to satisfy some software contract. Then we run this on a hardware machine that we verify to satisfy a hardware contract to get end-to-end guarantees. Because this type of isolation, we have to ask the question of, can we leverage isolation to actually weaken the software requirements and assume weaker attack models? Ultimately, it's an open community challenge to determine what the space of useful hardware software contracts is that balances restriction on hardware and software with performance. Thank you.